Hello everyone, my name is Sachindra Dahal. I'm a Ph.D. student at University of Illinois at Urbana-Champaign. Today I'm going to present about passive sensing of conductive concrete for vehicle lateral positioning. So connected autonomous vehicles have arrived in different shape, size, form with different promises. They provide increased driver and passenger safety, increased roadway capacity, improved mobility for elderly, disabled, and youth. And they also provide decrease in traffic congestion and fuel consumption. So to discuss about how CAVs work, they have two parts, the connected part and the automated part. So the automated part consists of sensing, planning, and acting. So the sensor senses the environment, then the machine learning algorithm or computer vision algorithms, they plan the path based on that, and the actuators would execute the command given by these algorithms. And again, there is the connected part, which consists of DSRC or cellular method to implement vehicle to everything communication, basically vehicle to infrastructure, and vehicle to pedestrian methods. But the problem is when we have adverse weather like snow, rain, or fog, the sensing part of the automated section, it gets affected. And also the current vehicle to infrastructure approach, it just focuses on roadside unit or traffic lights. So the biggest infrastructure, the road itself, is missing in action basically. So to discuss about how the CAVs stay in lane, currently they use GPS as a primary sensor, which gets coordinated from satellite. But the problem is the error is around 20 feet while the lane is just 12 feet wide. So the vehicles also use camera using computer vision to find the lane markings and stay within the lane where the GPS tells it to. So basically it is sensor fusion of GPS, camera, LiDAR, existing maps. So using a redundant information to predict better is how they achieve this goal. But one big problem is improper lane marking. Not everywhere there is very good proper lane marking. And another problem is even if there is a proper lane marking, there is bad weather, which affects the camera. So lane markings are not visible or signal of GPS is worsened. To put into context, 33 states receive more than 10 inches of snow annually. Or for example, in February 2019, 60% of the US was covered in snow. So weather independence is needed for large-scale deployment of CAVs. So the question arises, are the roads smart enough right now? The answer is no, because they don't communicate with CAVs. So roadways can actually supplement the current CAV sensors to improve lateral positioning, even when the condition is bad or adverse. So how can we achieve that is by using passive sensing. We can create a repeatable electromagnetic signature, which is pretty unique and can be identified by the autonomous vehicle. And we can create those signals in the pavement by using construction materials that's commonly used in pavement industry, like steel fiber or steel slag aggregates. We don't have to use expensive or sensors or something that consumes power or needs a lot of wiring. So I'll discuss about the lab testing that is going here at UFI. So we use a sensor, which is induction-based eddy current method, and it creates a alternating magnetic field using a 10-inch diameter coil at 200 Hertz. So whenever a metal target is brought into this field, it induces an eddy current, which is detected by the sensor. So in our case, it is a steel fiber reinforced concrete. So how we test it is we prepare a slab. We have made a slab which is 18-inch wide, 18-inch in length, and 6-inch in height. And on the top of the middle surface, we have made a notch which is 1 inch by 1 inch, or 2 inch by 2 inch, or 3 inch by 3 inch in diameter. And what we do is we make an electromagnetic prism or a concrete prism that has steel fiber in it, and we make those prism of the exact size and put it into this and do the testing. So we mount the coil on a motorized frame and the sensor is driven at a fixed height above the slab, and it is moved at a constant speed to collect the data. And in addition to the normal surface condition, we also test it in a different adverse weather condition, which is created by having a plastic container, which is not electromagnetic, and having a 0.5 inch, 1 inch, and 2 inch of ice or water standing on the plastic container and with the testing. So I'll present some of the results that we get when we pass the coil on top of the slab transversely. So this is an example signature. So what we observe is, so there is this electromagnetic prism, and as we move the sensor above, the highest signal is achieved directly over the electromagnetic material. And as we move offset from that electromagnetic material, the signal drops out. So this is an example where we change the height of the coil or the height of the sensor above the slab. And when we increase it from 5 to 6 to 7 inches, the signal decreases. So there are different factors that would attenuate the signal that we achieve. So to test that, what we did is we created different factors. One is sensor height, electromagnetic prism, steel fiber content in the electromagnetic prism, having water or ice on the surface. So we changed these parameters at 3 different signal attenuation level. So having a lowest signal attenuation gives us the best signal basically. And we increase each of these parameters and see how the signal deteriorates. So for example, this point is when the coil height is at 5 inches, steel prism size is 3 inch wide, and we have 1% of steel fiber without ice or water. We get this signal, and we just change each of these parameters and see how the signal attenuates. So what we observed is these 3 parameters, which are prism size, sensor height above the slab, and the fiber content, it attenuates the signal highest. And these are the factors that can be controlled during the design. We can say what size of prism we need in the road, at what heights can we implement or put the sensor in a vehicle, or what content of fiber we can put in the road. The factor of water, when we had 2 inches of water standing on the slab, it was still detected. It attenuated by 23%, but the signal was still detected. And when we put 2 inches of ice on the surface, we did not see any signal attenuation. That's because ice has a dielectric constant of 3, which is similar to that of air, versus water, which has 81. So in conclusion, we can strategically modify the pavement material to create electromagnetic signature that is repeatable and can be detected by CAVs. From our research, it was found that some of the highest signal attenuation parameters can be controlled in design process. The strong signal was still detected when the adverse conditions were present. And for the future, the roads can be designed not just for the physical properties, but also for the electromagnetic properties to help connected and autonomous vehicles. And I would like to thank CCAT for the funding for this project. And thank you, and I'm open for any questions.
Thanks. So we have about 5 minutes for questions. So first, I'd like to start with questions from the judges.
I have a quick question. I was just wondering what happens on pavement which is over, say, a bridge which is already metallic. It's a metallic truss.
All right. So over a metallic bridge, or for example, CRCP, I can show you a slide. I prepared a slide for that. So basically, when there are a lot of reinforcement present on a pavement, what happens is, as our research showed, that the coil height would highly affect the amount of signal. So although these signal would be highest, but we have a metallic signature on the surface, which would give us slightly higher. So when we look at the lateral profile, we would still get a higher signal at the location where we plan it to get.
Okay.
I had a question.
Hi,
My question, sorry.
Mm-hmm.
My question is, so the sensor placement seems like it's important. Can you place the sensor, or are you placing the sensor to test so that the car can distinguish between individual lanes, or it's just plain distinguishing where is the road and where is not the road?
It is basically it is identifying where exactly the vehicle would be on a road laterally. So instead of just one sensor, we would have an array of sensors, and the sensor that reads the highest, which would, for example, if it is in the middle of the car, it would read the highest signal. We would know based on which sensor reads the highest value, we would know what part of the car is in the center of the lane, basically, if I answered the question.
Yes, I'm still a little confused how you are designing it. So yes, I understand that you can place multiple sensors and you will know, which sensor you're getting the signal from, but how would the car know where exactly are the sensors, the position of the sensors on the road?
So if we have, well, we don't have sensor on the road. The material on the road is always in the center of the lane of the road. So based on the sensor location in the vehicle
Oh, the
itself,
sensors looking on the vehicle, okay.
yes. So based on that sensor location on the vehicle, it would know where it is getting the highest signal from
Okay.
the electromagnetic signature. And based on which sensor is reading the highest, it would know what part of the vehicle is at the center of the lane.
I see. Okay.
Mhm.
So I'd like to ask a question about construction materials briefly, if you don't mind. So in a couple of different regions, especially here in the colder climates, there's been talk about going from steel rebar going into carbon fiber. Have you been able to, is this type of use case going to be applicable with carbon fiber rebar as pre and post tensioning, or will this completely change the way that the sensors interact with the materials?
For the carbon fiber rebar, we have not, or reinforcement, we have not tried those materials, but some of these can be also produced by infusing different metallic particles. So as long as the construction material is infused with certain metallic particles, it would detect that. So just using the traditional carbon fiber would not, I assume, provide the signal. But yeah, if it can be modified with infusing certain metallic particles, it would definitely be able to identify that.
Talking about the slag introduction into slag into the concrete.
Yes.
Okay.
Or steel fiber.
Understood. My second question is, and this may not be relevant now, but just something to think about is, what about overall cost? Introducing this into already expensive evolution. I mean, what kind of cost can we expect into this type in a real world scenario?
So basically, these things can be done in steps. For example, wherever there is rehabilitation of a road, we can do it in an overlay type of thing. So I did the cost calculation. So if we are using 3" by 3", for example, the size of the prism, and using 1% of steel fiber to construct 1 mile of road, it would be around $125. Including the concrete material and the steel fiber for 1 mile of road, which is not as significant. But if we want to retrofit it actively, we might have to wait for the right time to do the pavement rehabilitation. That might be the ideal time to do this type of thing, rather than going and destroying or making grooves on the road and filling it. We can wait till the roads are ready for retrofitting, and we can do this with an overlay system. But by the calculation, it's around $125 per mile.
Great, thank you.
Mm-hmm.
We have a question from Al Leeds from WCC. Any data on the signal attenuation effects of the mixture of water and salt/sand?
We have not done those right now, but we plan to do that. For this type of thing, we have a paper related to this exact thing that I would be happy to provide. But we have not done exactly with the salt and water, but we have done it with water and ice right now. But I've tested, although not for the paper, I've tested it, and it does not attenuate the signal significantly. It attenuates somewhat similar to how water does, because water has dielectric constant of 81, which is very high compared to having salt and water.